So what else is PA equals LU useful for? For one, it's incredibly efficient for solving systems of equations. So if you just give me a matrix A and you want me to solve a system as quickly as possible on like a computer, PA equals LU is the right tool for the job. So let's say that we have a PA equals LU factorization, and then let's say we're studying the system AX equals B. So our system looks like AX equals B. And now to take advantage of PA equals LU, I'm going to multiply both sides of this equation on the left by P. Well, that introduces a factor of P times A on the left here. And the whole point here is that P times A is L times U. So that PA is the same as L times U. So now the system we're studying, AX equals B, is the same as LUX equals PB. And so here's what people do. They introduce a change of variables. They say, let's set U times X equal to Y here, and then let's break this system into two different parts. Let's solve L times Y equals P times B for Y. Then we can solve for X by using U times X equals Y. And the reason for breaking the problem up like this is that when we go to solve Ly equals PB for Y, L is a lower triangular matrix, so that system is actually easy to solve. We just look equation by equation, solve for a variable, and then substitute into the next equation. Once we have Y, we can then solve for the desired vector X by studying Ux equals Y, and U is in row echelon form, and row echelon form systems can be solved with a similar method. Solve for a variable, sub into the next equation, so on and so forth. So the big takeaway here is that if you have PA equals LU, you can take the system AX equals B, which is likely difficult to solve, and you can chunk it into two smaller parts. First, we solve Ly equals PB for a vector Y. Then we solve Ux equals Y for the desired vector X. Let's see this play out with an example. So in this example, someone is giving me PA equals LU, and they're giving me the vector B. The vector B here is 0, -3, -1. Just for the sake of review, let's remind ourselves a few of the key intelligent things we can say about this matrix A because we're given PA equals LU. Well, A is 3 by 3, and it looks like U here, which is in row echelon form, has rank 3. So that actually tells us that A also has rank 3, so consequently A is non-singular. So if I wanted to solve AX equals B, one thing I could do is work from scratch and augment A with B and do Gauss-Jordan and get a result. I could also try to find the inverse of A because I happen to know it exists here. That would require augmenting A with the entire 3 by 3 identity matrix, row reducing, and then finding the inverse, and then multiplying the inverse by B. We're proposing a new point of view, which says, take advantage of PA equals LU here to break this system into two easier systems. So the first step of solving AX equals B, when you have PA equals LU, is to solve a new system, Ly equals PB, for the vector Y. So what you're looking at here is the system Ly equals P times B. So L is this lower triangular matrix, and what we're seeing here is that we're using that as the coefficients matrix for a system where the variable vector is Y. So Ly looks like this. What about on the right-hand side here? This is P times B, which is obtained by taking the permutation matrix in our equation, P, and multiplying by B. So we're going to solve this system, and the thing to appreciate here is because this system is lower triangular, I can systematically solve for each variable one at a time. So if I look at the first equation here, the first equation is just telling me y1 equals -3. I can then take that value of y1 and substitute it into the second equation and use that to solve for y2. If I do that work, I end up with y2 equals -9. And then finally, I can take my values of y1 and y2 from that I found in the first and second equations and place them into the third equation and solve for y3. In this case, I get y3 equals 50. So now I have solved for y, and the next step is to solve the second system, which is ux equals y, and I'm solving for x now. So where is this system coming from? Well, here, the coefficient matrix is coming from u, which was part of my original data. So this is u times x. And now I'm setting this equal to y, and y was the vector we just solved for in the previous step. This system is not lower triangular, but it is upper triangular. So instead of working my way from the top down, I can work my way from the bottom up, solving for the various variables. In the last equation, I can cleanly solve for x3 to get x3 equals 10. I can then substitute x3 equals 10 into the second equation and solve for x2. When I do the arithmetic there, I get x2 equals 49. Then I can go to the first equation and take my values of x3 and x2, put them into the equation, and solve for x1. Here I end up with x1 equals negative 37. So when all is said and done, I've managed to use these two easy systems to solve the original hard system involving the coefficient matrix A. The punchline is that the vector x that solves ax equals b is the vector negative 37, negative 49, 10.